This is part 5 of the tutorial on type classes. In previous parts, we talked about how type classes can have derivation patterns, and up until now, we have not been talking about type class laws very much. But actually, almost all type classes have laws. There are type classes without laws, but many interesting type classes, such as monoid, functor, applicative, and so on, have laws. So describing the laws of type classes is not very easy, and much of the effort here is to try to find convenient techniques for reasoning about type class laws. So here's an example of what type class laws we might want. So generally, type class laws are some equations that the methods of the type class must satisfy. For the monoid, we have 3 laws. So monoid type class has 2 methods, as usually formulated, mappend and mempty. And so we can write equations like this in a notation that is more mathematical and shorter to read. These are the 3 laws. So for any x, which is a value of a monoid type, for any y, for any z, which are values of the monoid type, and e is the special value returned by mempty, so we denote it just by e for brevity. Then we have these laws. So the operation plus, which is denoted here just again for brevity, is the mappend. So mappend of mempty and x. It is written like this. And that should be always equal to x for any x. And similarly this. And then the associativity law. So these are the 2 identity laws, the left identity law and the right identity law. And then the associativity law. Note that there is no commutativity law or any other laws at this point. So usually we do not impose them for a monoid, but in practice many monoids will have more laws, such as, for instance, idempotency law, that x plus x is always equal to x for any x. So there might be other type classes with monoid laws and extra laws on top, which are formulated with more equations. So in generally there is one or more equations for the functions that are methods of the type class. And in our formulation of type classes for the purposes of the theory, we unite all of those type class methods into a single value, which we call the structure map, which is for algebraic type classes is a function of type pt to t, where t is the type class member type. So actually it's not very convenient to reason about laws when they are formulated as separate equations. It turns out that we can reformulate the laws in a more abstract way with some more work, and then the advantage is that we can reason about the laws much more easily, but the price is that we need to learn about more theory, especially about functor algebras and monad algebras. The good thing is that there isn't so much theory other than definitions. So functor algebras I already described. They're just functions of type pt to t. From the programmer's point of view, that's enough to know, and we will just talk about functor algebras and monad algebras in terms of programming, in terms of types and functions. So there's nothing else that the programmer really needs to know in order to be able to understand the properties of these functions. So what are monad algebras? So suppose M is some given monad, and I will use this notation where the methods pure and join. Then a type T together with a structure map of this type, which is just like a functor algebra structure map, is called an M-monad algebra. So when the following two laws hold, so it's not just that you have this function. For a functor algebra, that's sufficient. For a monad algebra, it's not sufficient. So you do need to have the structure map. And also you need these two laws to hold, the identity law and the composition law. To illustrate what these laws do, here are some type diagrams. The first law, it takes a value of type t, and it lifts it to an empty via pure, and then evaluates the structure map and gets back the t. And the law says you need to get back exactly the same value that you started with. And note, I'm writing this in a kind of Haskell-like notation, and so the order of these functions is the opposite. Excuse me. The order of these functions is opposite. So first we write mt, which is the last function here, and then pure. So you need to read it kind of. So in my book, actually, I use a different notation where I have a straightforward left to right composition. First I write pure, then I write semicolon, and then empty. Anyway, but here I will keep writing this because it's not so important. I'm not going to do a lot of derivations here. The second law is the composition law, and it begins with an arbitrary value of type m of mt, where t is an arbitrary type. And then we flatten this, so join it into just a single layer of m. Then we evaluate in the structure map. We get a value of t, type t. And we can also get that value by applying the structure map twice, one under f map. So we apply it here, we get an mt, and then again apply the structure map and get a value of type t. And the law says we should get the same value both ways. So why is this law interesting? Because it turns out that these two laws can be used to enforce typeclass laws. And here I give an example in detail, which is a simplest kind of interesting, non-trivial example with the monoids laws. Often typeclass laws can be expressed like this. In some cases it could be very difficult to find the monad that has the right properties, but I will talk about it a little later. For the monoid laws, it turns out that the monad that you need to choose is the list monad. So the list monad has the methods pure, which gives you a single element list, and join, which is just list concatenation. What does it mean that a type T is a list monad algebra? It means that we have the structure map M of type list T to T, and then we need to assume the laws of the monad algebra. So the laws shown in the previous slide, we assume that they hold for this function M and for this type T. So then it turns out that we can derive from these assumptions the monoid operations and their laws, the two identity laws of the monoid and the composition law of the monoid, which is not obvious, right? Because there are very different kinds of laws. Here we have two laws which have this very different form, and for the monoid we had three laws which had this specific form. So how can we derive that? It turns out we need some ingenuity to derive this, so we try to apply the structure map to different arguments, so to lists. So the structure map is of type list T to T, so let's apply it to different kinds of lists, to an empty list, to a single element list, to a list of 2 elements, of 3 elements, and so on. Let's try what happens and apply the laws and see what kind of properties we can derive from that. And the result is that let's let's say, so M of the empty list is just a value of type T, which we can just denote it by E for convenience. It will turn out to be the empty element of the monoid. And then what is M on a single element list? It turns out by identity law, it must be that value itself. So identity law forces that, because the pure of X is this. And then M of pure must be identity. And so we must have this property. Now, what is the M of a list of two elements? We don't know. Let's denote it as this binary operation. This will turn out to be the binary operation of the monoid. Then we can proceed again. Okay, so what if we apply this we apply the composition law to this kind of initial value. So composition law is a law that applies to initial values of type M of mt, and then we apply these functions, and then you get the value of type t, which must be the same. So what is this initial value of type M of mt? That is supposed to be a list of lists. So let's take this one, for instance. And then we apply the left-hand side of the composition law and the right-hand side of the composition law. And the left-hand side gives us this, and the right-hand side gives us this. So then, because they must be equal by law, then x must be equal to x plus e. So we have derived the right identity law. And similarly, if we put first the empty list and then x, we'll derive the left identity law. And now let's try to apply it to this kind of argument, list of lists with this form. And then we find that the left-hand side of the composition law gives us this. And we don't know yet what that is, but okay, we'll just keep it like this. And then the right-hand side of composition law gives us this expression. And that is already interesting, because then we can also use xyz in a different order. First a list of x, and then the list of yz, and then we'll get this. And so essentially we have derived in this way that this expression is equal to that, which we don't know what it is, but it's equal to that. So this is the associativity law of the monoid. Now, what turns out after this point is that no matter what other arguments you put into the composition law, no matter what other nested lists, they can have empty or non-empty nested lists, no matter what you put in, the composition law will hold, assuming that these three laws hold. So the identity law and the composition law of the monad algebra are now satisfied. So there are no more monoid laws that you derive from them. So that you need to prove, of course, that you haven't missed any more laws. So I will not show that proof now, but it seems to be intuitively clear. So this function is actually similar to a fold, to reduce, not to fold. It's similar to reduce. So reduce a list with a monoid elements to a single monoid value. And then clearly this reduce of an empty list is the empty monoid value, and the reduce of a two element is the monoid operation, and the reduce of any number of elements is just a monoid operation applied to all of those elements in order. And so this clearly can be proven by induction, that all other arguments that you can put into the composition law will satisfy the composition law from now on. So once the monoid laws hold. So in this way we have derived monoids laws with some ingenuity from the laws of the monad algebra. It's by no means directly obvious that this is true, but this is the interesting trick. And this trick can be directly generalized. So what we have found is that if any type T is a list monad algebra, then this type T belongs to the monoid type class. It has the monoid operations, which we derived in the previous slide, and it satisfies the laws of the monoid. The operations are lawful. And this seems to be directly generalizable. For some monad M, so instead of list, we use a different monad M, maybe. If T is an M monad algebra, then T belongs to some algebraic type class instead of a monoid. To remind you, that's a class whose methods can be combined into a single value of this type, Pt to T. And this, of course, opens up interesting questions. To which type class? So if I give you monad M, to what type class do these monad algebras then all belong somehow? And for what functor P? For what structure functor P is that going to be? What are going to be the operations of that type class? And conversely, if I have an algebraic type class, can I find this monad M that magically will impose the right laws once I demand that the type is an M monad algebra? Both of these questions are very difficult, and I will not be able to answer them fully in this. I will answer partially, but essentially there are structure theorems, which I will explain, that partially answer these two questions. And the structure theorems say the following things. So first of all, actually M is the free instance constructor of that type class. So this is the deep result that is very much not obvious. We know that for monoid, the free monoid constructor is list, we know that. But this is not a coincidence, that list monad algebras induce the monoid type class. That is not a coincidence, this is a general fact. If M is a free instance constructor of a given algebraic type class, then M is a monad. With that monad M, we can talk about M monad algebras by the definition that I gave. If T, any type T, is an M monad algebra, then T belongs to the type class. It has the methods and the laws. And finally, if an algebraic type class has no laws, then we can say what that is. So it's just methods M with Pt to T. We take the free monad on P, and that's the monad we need to say that if T is an M monad algebra, then T belongs to this algebraic type class that has no laws. So in the case when there are no laws, we know how to answer these questions. Given P, find M, and given M, find P. Because you look at M, and if it's a free monad of something, then you know that's the type class and it has no laws. But other than this, for type classes that do have laws, it's really not obvious how to find this monad, and vice versa. Given a monad, it's not obvious how to describe all its monad algebras. However, this approach gives you an advantage that it's a much cleaner general approach. You're talking about functions that are very general, that have simple type signatures like Pt to T, Mt to T. You are not talking about some difficult specific equations with unknown variables x, y, z, and you don't care how many laws there are. There's just one equation that shows all the laws at once. Category theory is like this. So you generalize, and then some things become easier. So we're not really going to do category theory in this tutorial, but I just want to mention that this is a technique that is inspired by category theory. That it tells you, okay, well, maybe if I reformulate something like this, then I can get interesting results. There are difficulties, certainly, such as that the free instance constructor has to be derived by hand separately for every algebraic type class. There is no general method to find M, the monad M, that is suitable to enforce the laws of any given type class. So for specific type classes, we have, with some work, found those M. But in any case, it's not clear that we will always find such a monad M within our type system. It might be a monad that needs very complicated types, maybe even dependent types, maybe quotient types, or something very difficult that we don't have within our programming language. And even if we go to a programming language that has those features, it could be very difficult to find that monad anyway. So these are the caveats, but for many cases we know what M is, and this gives us a much easier approach to reasoning about type class laws in general. So let me indicate some things. I will not give a lot of proofs here, but I will indicate what kind of knowledge we get. So let's work with an algebraic type class that has a fixed structure functor P, and suppose we know what that free instance constructor must be. That's a monad M. Always a monad. So that's also actually very interesting, in my view, very elegant result, that this free type class instance constructor is always a monad. Like free monoid is list, and free semigroup is non-empty list, and free whatever is always a monad. Now, like if you're asking what about free applicative? Now, free applicative is a constructor which is higher-kinded, is a type class constructor. So it takes a type class and gives you another type class. Sorry, I'm confused. A type constructor. It's a type. It's a constructor at the level of type constructors. It takes a type constructor and gives you a new type constructor. And so at that level, it is a monad, so to speak, in the category of type constructors. But it's not a monad that we will use necessarily in code as a monad. So by definition of the free instance constructor, we have certain properties, and one of them is that we have this evaluation map MT to T for any type class member T, and it must be a unique type class preserving function of this type. So that is a definition of what a free instance constructor is. And using this property, we can prove that it is a monad. So how will we show that? Let's consider that instead of T, mu. So let's set T to mu, where u is any type. Then this function will give us this kind of function, m of mu to mu. And this must be a unique type class preserving function of this type. So this is obviously the join method of a monad, and the laws for this method can be derived from the uniqueness property. So for instance, the associativity law of join is m of u transformed into m of u. And that's again a type class preserving function, so it must be unique. And this uniqueness tells us that the left-hand side of the associativity law is equal to the right-hand side of the associativity law by uniqueness. So this is a very interesting. I'm not going to give the details here, but this is the approach and the value it gives. So the join method, the pure method, is also there because a free instance constructor must have a way of lifting values of type T into the free type class. So that lifting method is the pure method, and it will satisfy also the laws with some technical assumptions that I'm omitting here. But in the book, in chapter 13, I will write everything out once I get some more time. It turns out that type class preserving maps, as we have seen, they're just P algebra morphisms. But if we are looking at M monad algebra morphisms, then it turns out that there are one-to-one correspondence with the P algebra morphisms that obey the laws. So in other words, type class preserving maps between types that obey the laws are not just P algebra morphisms, but they are M monad algebra morphisms. So this gives us kind of a picture that an algebraic typeclass without laws is just P-functor algebras with their morphisms, and the category of P-functor algebras, in other words. And algebraic typeclass with laws is M monad algebras and their morphisms. So this is a categorical view of typeclasses. The algebraic typeclasses have these representations, and from this you can start deriving interesting properties properties that are actually relevant for programming, not just theoretical properties. For example, if you have a surjective functor algebra morphism, then if you know that the laws hold here, then you also know that they hold there. So the P functor algebra morphisms enforce laws as well. It is relevant because sometimes you use types that are not necessarily law-abiding. So, for instance, free monads or free something else, you could construct instances of free functor, free monad that do not actually obey the laws. And sometimes you need that, and sometimes you want to ensure that later some things will obey the laws. And for that you need to be careful, but the theorems tell you that, for instance, as long as you have this monad algebra morphism, then it will enforce the laws in T as long as they hold in MT. So they hold in MT, then they are enforced in T. But in case they don't hold in T, but they hold in U, then it's okay, because you have this other property that violations of laws become invisible after you apply a typeclass preserving map. In other words, an algebra morphism. So typeclass preserving maps is something that programmers can write down in code, just making sure that operations are mapped into operations recursively. And so if that is written, then the programmer has assurance that after applying the evaluation function here, the laws will hold, and the violations of laws in some intermediate data structures are going to be invisible. So this is just kind of an inspiration. I'm not going to go into details in this material, in this slide, because it's quite technical. It needs to be supplemented with lots of assumptions and technical details, which I will all write out in my book. So far I've been talking about algebraic typeclasses, but exactly the same thing happens with coalgebraic typeclasses that have this kind of structure map. And their laws can be expressed via comonad coalgebras, which are similar to monad algebras except for reversing them the errors in many places. And they also have these structure theorems. If M is the co-free instance constructor, then it's always a comonad. Then if some type is a comonad coalgebra, then it belongs to the type class. And if a coalgebraic type class has no laws, then we know what that M is the co-free comonad on P, on this structure functor. And just as in the case of the algebraic type classes, it is not obvious how to find M given a coalgebraic type class, and it's not obvious how to find the type class given M. It requires some ingenuity and some manual derivation in each case. So, for example, what is the co-free comonoid constructor? What is the constructor which is going to be a comonad that generates laws for the co-free, generates laws for the comonoid? And a comonoid is is a type class where you have a single method from t to pair of tt. So the monoid had a method which combines tt into t. Comonoid takes a t and gives you a pair. So it's kind of a converse method. And it has also an associativity law that it needs to satisfy. There are no identity laws. There's no identity element here. There's a comonoid is in some sense simpler, but for instance, I don't know what is the co-free comonoid constructor, which comonad is that, and I don't know how to find out. So it needs to, some techniques need to be developed for this kind of work, and I wasn't able to find the answer. So in any case, it's not obvious. So now we're going to get into how to prove the algebraic derivation patterns. So that will be the next and last part of the tutorial.